Today we are considering the effect of scale factor scaling up, or enlarging, or scaling down, reducing, on perimeters, areas, and volumes. Nothing new, but because this is one of the newer overall concepts to this book and can be challenging in understanding how to go about it each time, they give us a review lesson where we put it all together. Remember that when you consider the ratio of a new perimeter and an old perimeter, that ratio will end up just being scale factor. So if you double or scale factor of 2, then if it's a bigger one, it will be bigger because it's a scale factor of 2, then maybe the original was 3 in length, then your new one is 6 because you doubled it, and that divides out to the scale factor. Let's say you have a perimeter of 10. Okay. If the scale factor is 4, then your new perimeter is just the original times the scale factor. If you're reducing and you have 10, and let's go with 4, but 1/4 this time, then we would need to divide 10 by 4, which would be 2.5. So every length is 1/4, and your overall perimeter might be 2.5. So that's perimeters. They're pretty simple. It's just literally the scale factor, whether it's 2, 3, 4, whatever. But then you take that scale factor and you square it with areas because it's 2 dimensions. So length times width squared. So if the perimeter was 2, that scale factor squared means its area would be a 4 scale factor, meaning 3 times 3, area of 9. That area for the bigger new version of a scale factor 4 would be 36. So if the perimeter is twice as much, the area is actually 4 times as much. Or if the scale factor is 3, well, the area scale factor is the way you can think of it as squared, so that's 9. Area is times 9, so if I have a area of 4, again, the new area would be already 36, even though the original was only maybe a 2 by 2 square. Because you need to square the original scale factor, your new version would end up being 36 in the middle, which could be a 6 by 6. Okay, see kind of what we're doing here. And then in 3 dimensions, length, width, depth, you get scale factor cubed. So if the scale factor, the one we get the most often because it keeps it small, if the scale factor was 2, as in you got from 1-inch cubes to 2-inch long cubes, okay, perimeter only doubled, area would have quadrupled because it's 2 squared, right? Volume is cubed, so the scale factor for volume is to the 8. So this volume of the original was just 1, because 1 times 1 times 1. I guess we could say 1 cubed. Now we take 1 times the new scale factor. I think I said to the 8th. I meant times 8. Sorry. So the new volume would be 8. And we see that up here because it's going to be 2 times 2 times 2. Right? Length, width, and depth is 2. So if the scale factor is 2, the area is times 4, the volume is times 8, and we get that by squaring and then cubing the original scale factor. In example 1, they keep it simple. Vince is asked to paint a mural. So he buys 10 times as much paint because the new mural is supposed to be 10 times the length and 10 times the width. That means a scale factor of 10. And yet he runs out of paint. Why is that? Because painting is a two-dimension, length and width, as they said, length and width two-dimension project. So we're dealing with which one? Perimeter, area, or volume? We're dealing with area, which means everything gets quadrupled on a scale factor of, well, not quadrupled, but times 100, right? Because it's a scale factor of 10. We square that for area. That means the scale factor for area needs to end up being a ratio that comes to 100. So if this area had been, let's say, 2, the new area needs to be 2 times 100. The new area would need to be 200. So why did he run out of paint? He needs 100 times as much paint when you're dealing with length and width, because it's length and width square. I'm just trying to say it over and over in different ways so that you kind of catch on. So if it's dealing with area, you need scale factor squared. So 10 squared in that case. Irene's working with stained glass. Once again, it's in two dimensions because she's going from a bigger to a smaller, which means it's a reduction. Scale factor of 1/3 makes it smaller, right? So you go from the original times, I'll make this obviously an O. Original times 1/3 gives you new, because this is the scale factor. Now that's in one dimension. She's dealing with, well, let's start in one dimension. If the perimeter is 240, that means the new one, because it's only perimeter, it's only distance, one dimension, then we just divide that by 3. The new is 80. But with squared, we take scale factor squared, which means 1/9. 1 times 1, 3 times 3, right? 1 squared, 3 squared is how you find that. Or you can think of it as 1/3 times 1/3. So that's 1/9. That's the scale factor for area here. Then we take the original area, which is 3, 4, 5, 6. Multiply that by 1/9, which means we'll end up dividing 3,456 by 9. That's the new area. That's how much glass she'll need for her replica. That comes to 384 inches squared. And then, of course, we have to have a volume 1. 1 inch cubes. How many cubes are here in the picture? One's hidden. Careful. Looks like 1, 2, 3, and hidden underneath there, because this one cannot float, there's one under there that's 4. So if there's 4 cubes, how many 1 inch cubes will you need if dimensions get doubled? What's the scale factor in one dimension? Always identify that first. Scale factor is double, 2. What would be the scale factor for area? 4. Now what's the ratio of volumes for volume? We're going to take this cubed. The scale factor for volume is 8. So all you have to do in this volume problem is take, how many cubes were there? Multiply it by the scale factor for volume here, which is 4 times 8. 32. Don't forget labels. All right. Explain how it is we found different scale factors in letter A. Then do letter B, D, and F. Best of luck.